Hello everyone, this is Vani from R.M.K College of Engineering and Technology. In this video, we are going to discuss about mutual information in information theory. So objectives are to recall what is information, to define what is mutual information and its properties. In order to define information, there are two approaches, intuitive approach and mathematical approach. So in an intuitive approach, we can recall that more uncertainty leads to more information. That is, information contained in any event is inversely proportional to the probability of occurrence of that particular event. So mathematically, the amount of information gathered after observing an event is given by I is equal to log of 1 by P with base 2 if it is represented in bits and if base E if it is represented in natural units. So the relationship between uncertainty and information is nothing but occurrence of a less probable event conveys more information. So if we consider a random variable x with possible outcomes of xi, I is equal to 1 to n, then the self-information content of the event is defined as I of xi is equal to log of 1 by probability of xi which is represented as minus log of p of xi. So information and probability are inversely proportional to each other. So in order to define mutual information, if we consider two discrete random variables x and y, the meaning of mutual information is nothing but how we can predict y if x is given or how we can predict x if y is given. So there exists mutual information between two events x and y. So we can interpret this mutual information by taking some practical day-to-day examples. The first example, if we take DNA sequencing, the correlation between two DNA sequences is nothing but mutual information. One sequence can be predicted from the other sequence. This process is nothing but again mutual information between two sequences. Similarly, in the second example, the relationship between disease and DNA code is again mutual information. We can find out the disease existing in a DNA code through mutual information property. The third example is Bombay Stock Exchange mutually related with London Stock Exchange. The rise and fall of Bombay Stock Exchange is related to London Stock Exchange. So this again leads to mutual information example. So in order to define mutual information, if we see that X and Y are independent, already we have seen that mutual information is nothing but one event is given and we are finding out the other one. If they are totally independent, then I cannot find out what is Y given X. And the other way also, I cannot find out what is X given Y. So there does not contain any information, any mutual information between X and Y if they are independent. So that is represented here. Now, if X and Y are fully dependent events, then I can find out what is X given Y and vice versa. Hence, there should be some relationship between X and Y. That is, we call it there should be dependent events in order to find out mutual information between two events. Now, mathematically, mutual information is represented as I of xi semicolon yj, that is I of xi yj is given by log of probability of xi by yj, which is nothing but conditional probability divided by probability of xi. Here also the units are same as information, either bits or e. If we are using bits, then it is represented as 2, and if we are using natural units, then it is represented as e. Now, one important property of mutual information is it is symmetric in nature. So let us see how it is symmetric in nature. Now, I of xi comma yj is nothing but log of conditional probability of xi divided by probability of xi. So if we take this part, this right hand side part, probability of xi by yj given probability of xi, we can multiply both sides, numerator and denominator, by probability of yi. This is just for mathematical manipulation. So the numerator is nothing but becoming joint probability, probability of xi comma yj divided by probability of xi, probability of yj. So again, this can be represented by probability of yj given xi divided by probability of yj. So if we compare these two expressions, we can say that the mutual information is symmetric in nature. That is, I of xi comma yj is equal to I of yj comma xi. The properties of mutual information is very important in order to find out the channel characteristics. So the first property is mutual information of a channel is symmetric in nature. That is, I of x comma y is equal to I of y comma x. The second property is that mutual information is non-negative in nature. That is mathematically represented as I of x comma y is greater than or equal to 0. There can be no mutual information or the mutual information is positive. Mutual information can also be expressed in terms of entropy of the channel output, which is given by I of x comma y is equal to h of y, which is the entropy of y, minus h of y given x, which is nothing but conditional entropy. And the fourth property of mutual information of a channel is related to joint entropy of the channel input and channel output. So it is given by I of x comma y is equal to h of x, which is entropy of x, plus h of y, which is entropy of y, minus joint entropy, which is h of x comma y. So, in practical application of mutual information, in information theory, it plays a major role in determining whether the channel is good or not in order to transmit the information.